Okay, in this presentation we're going to talk about swimming kinetics, and we're going to talk about swimming kinetics as it relates to application of biomechanics. In particular, we're really interested in triathlon and understanding how to select a particular wetsuit or why a wetsuit may influence swim performance. So let's talk about swim kinetics. When we do a kinetic analysis, we always start by identifying the forces acting on the swimmer. In this case, in swimming, we have gravity acting to pull down on the swimmer. We have buoyancy as an upward directed force pushing up on the swimmer. And then we have resistive drag and propulsive drag. And these are the two forces I really want to focus in on this presentation. And over here we have a little cartoon of that. We have a drag resistance, which is pushing against the swimmer, resisting forward movement. And we have propulsion force, which is acting in the same direction as the direction of the swimmer. And I want to talk about what's unique about each of these, as well as where they're similar. Now, I'm really interested in horizontal movement. We're not interested in the swimmer going up or down. We're interested in the swimmer going forward. So we'll look at just the equation, F equals ma, relative to horizontal motion. And we know in a kinetic analysis, the second step is to identify or put all the forces into this equation. So sum of forces acting on the object in the horizontal direction is equal to the product of mass of the person, or mass of the object, times the acceleration of the center mass. The two forces we're dealing with are propulsion force and resistance force. And I've got resistance as a negative force because it's going to be opposing the direction of movement. I could also rewrite this equation as propulsion equals mass times acceleration plus resistance force. The key with this is the more we reduce or lower the resistance force, the more kinematic effect the propulsive force will cause. And in reality, we have mass times acceleration. The swimmer is not swimming at constant velocity. The swimmer is constantly swimming up or speeding up and slowing down, speeding up and slowing down while moving forward. So we want to reduce these resistance forces as much as possible, and we want to increase the propulsive forces as much as possible to swim as fast as possible. And we've got different types of wetsuits. There's a separate video on wetsuit design. All right, we're in the water, obviously we're swimming, and water is about 800 times more dense than air. Now, it is dependent on temperature and what's in the water, in terms of salt water or fresh water or what particular matter is in it. But nevertheless, water is about 800 times more dense than air. The purpose of mentioning this is that everything that we've talked about with aerodynamics, that is drag force during cycling, maybe running, where we look at the resistance force due to air, it all applies to water, except we're just dealing with a much more dense fluid in water. All right, water also allows for buoyancy force. There's a separate video on buoyancy force, so please watch that, but that's the upward directed force, keeping the object afloat. And it is equal to the magnitude of the weight of the water displaced when we fully submerge the object. Now, there are different types of wetsuits. We talked about this, or I talked about it in a different video. This is a full sleeve wetsuit on the left and a sleeveless on the right. And these wetsuits have different advantages or disadvantages depending on who's swimming or why you're choosing why you're using one wetsuit over the other. In general, the full sleeve wetsuit is going to be faster than a sleeveless wetsuit, but sometimes a sleeveless wetsuit is more comfortable for someone and they want to use that. You just tend to use that in more warmer water versus colder water. Okay, so fluid dynamics is the general area of mechanics that we're dealing with. This is the science of flow of fluids, and we've been focusing on air and now water. Aerodynamics is just the study of motion of air and other gases. Hydrodynamics is what we're talking about now, the study of motion of water. And there are two classes of forces in fluid dynamics, the drag and lift. And really, I'm going to focus in on the drag force, even though lift can be important in swimming. There are all different types of drag forces in swimming. There's parasitic drag, skin friction, profile drag, there's lift-induced drag, there's wave drag. These are all worth going into, and this little cartoon on the right sort of talks about the complexity of drag forces. But what I want to do right now is just simplify our discussion of fluid dynamics, and especially in water, and focus just on a category of forces that I'll call resistive drag. I want you to know that this resistive drag can come from a variety of different sources during swimming. Now, if we had a little bit more time in the semester, we would go into these in more detail, but right now I'm really just going to focus in on resistive drag as a category. All of these are part of drag force. In fact, all these different parts are all part of the drag force equation. Now, the one type of drag force I want to zero in on right now is skin friction. Surface drag, also known as surface drag. This is the drag caused by the fluid flowing along the surface of a body, or over the wetsuit in this case. Some fluid, as it passes over the surface of the body, does not slide, but it actually sticks to the surface. Therefore, the smoother you can make this surface, or the more resistant to the fluid sticking to the surface, the faster you'll be able to go in swimming, or ultimately the lower the resistive drag force due to skin friction. All right, the other part of resistive drag I really want to talk about is the frontal area. This is also known as pressure drag or form drag. It's a little bit, I'm mixing some terms up a little bit, but I'm doing that on purpose. This is the area of an object that is exposed to the perpendicular flow, and that frontal area ultimately contributes to the drag resistance force. What happens is there's a turbulent flow behind the object, and that turbulent flow actually will cause a force in the opposite direction of the flow of the fluid over the object, and that ends up being the resistive drag force. When you talk about streamlining, or when swimmers talk about streamlining, that's causing a reduction of the turbulent flow behind the swimmer, and that's done by ultimately reducing the frontal area of the swimmer moving through the fluid. Okay, and this is a cartoon of the influence of frontal area on drag force. So here you have the top picture, which is a streamlined position, and there's very little turbulence behind the swimmer. And then the next picture is a larger frontal area hitting the water and more turbulence. That is going to be ultimately what's going to cause the increase in drag resistance force due to a greater frontal area being exposed to water. So let's look at the drag resistance force just using our equation. So drag resistance force, also known as fluid resistance. These are forces that oppose the relative motion of an object through a fluid. And we have air resistance forces, aerodynamic, that's more for cycling and running. Now we're talking about water, but it's the same equation. 1/2 rho CdA V squared. Fd is the drag force, rho is the density of fluid, Cd is the drag coefficient. This is a unitless parameter. And if you go back a few slides, you'll see some other drag coefficients that are included. This CD is just a general CD at this point. And then A is the frontal area. Now, collectively, we will refer to CDA in the real world because they're often hard to separate from each other, and they're easier to measure collectively. And then V in that equation is the velocity of the fluid over the object, and we square that unit. And units for drag force are units of newtons. So let's look at measuring drag resistance forces. We can do that using some pretty sophisticated instruments that are put in the water. Here's a picture of a system that I've used. This is a system put together by Hub Toussaint, who is co-owner of Hub Design. And this consists of a series of force platforms submerged in the water, and as the swimmer swims over this system, he or she grabs that force platform, and then that propulsive force is measured. Because we know there's two forces acting on the swimmer in the horizontal direction, propulsive and resistance, as long as we can measure one, we can know the other. Now the other term here that we do need to figure out is acceleration, but we can figure that out by knowing the timing of the swimmer going over each of these force platforms. So this is a neat way to measure drag resistance force during swimming. Here's some of the data resulting from using that type of system. On the y-axis is drag force in newtons, and on the x-axis is velocity. And we have three suits worn by a particular swimmer in this example. The one line in red is one suit, the line in blue is another suit, and the line in green is a third suit, or in that case the green line is a wetsuit. And each dot represents a swimmer swimming along the MAD system, and from that the drag force calculated for each of those velocities. So if we look at where that dashed yellow line is, we have an understanding from these data that this wetsuit would have this much drag force, but if we swam the same speed using a regular swimsuit, the drag force would be much higher. In this case, 11% higher. So a wetsuit will help a swimmer have less resistance force during swimming due to the combination of the buoyancy of the wetsuit and the smoothness of the wetsuit that reduces the CD. And the buoyancy is going to reduce that frontal area of the swimmer, and the smoothness of the wetsuit will reduce the coefficient of drag. So collectively, the wetsuit reduces CDA, which ultimately influences the drag force. Okay, so now drag force can cause propulsion. And there's several situations where drag force is actually causing propulsion. I mean, we've talked about a cyclist being pushed by a tailwind, or a sailboat where the wind is pushing against the sail, causing a boat to go forward, or blades of an oar during a rowboating. You put the paddle in the water and you pull on the oar, and that blade pushes against the water, and the water pushes against the blade to prevent the blade from moving forward. That's drag force. And that's what's causing the boat to go forward. Well, the same thing's happening in swimming. We put the hand in the water and we try to push against the water. The water resists that via drag force, and that resistance force is actually pointing in the same direction as the swimmer, and that is what's causing propulsion. So we'll say drag propulsive force, which is different than drag resistance force. Drag resistance force is resisting the motion of the swimmer. Drag propulsive force is causing the swimmer to move forward. Same exact equation for each of those forces, 1/2 rho CDA V squared. Now we can measure drag propulsion force, which is the same thing we do when we're measuring drag resistance force, but now we're actually going to just be focused in on the propulsive aspect of this. I have the picture of the MAD system on the right, and that measures propulsive force directly. The other two pictures are force transducers that are put in tow lines that a swimmer will pull against. And that's another way to measure propulsive force during swimming. And that's just some data of in the middle there on some propulsive force. The key is here that we can measure this, and then by knowing the propulsive force and knowing the acceleration of the swimmer, we also understand the resistance forces. Now there are lift forces when we start talking about drag forces, and these are perpendicular to the drag force. I'm not actually going to spend some time on this, but this does come back in when we start getting down to the finer details of understanding swimming propulsion. There are some lift forces that will actually help propel the swimmer forward. But we're not going to get into that right now. This is a Bernoulli's principle, but it is pretty important ultimately at the end when we're starting to look at the finer details of swimming. I'll mention the equation for lift forces, but I don't. I'm not going to ask any questions on this on an exam. But you'll see how similar it is to what we've already dealt with drag force. The lift force is equal to 1/2 CL A rho V squared. FL is the lift force. CL is the coefficient of lift. A is the frontal area of the body, rho is the density of the fluid, and V is the flow of the velocity over the object. So it looks a lot like 1/2 rho CdA V squared. Now, the order of those parameters doesn't matter. In this case, we've just changed the CD to CL. So wetsuits, why wear a wetsuit? Well, from a triathlete perspective, you wear in part to stay warm. Wetsuits do allow water inside them. That's why they're called a wetsuit. And that layer of water that enters the wetsuit is actually heated up by the body and gets warmer. And that warmth of the water ends up being an insulator to the cold water in combination with neoprene. So why does a triathlete wear a wetsuit? It's faster, so you can swim faster. Now there is some benefits for slower swimmers versus faster swimmers, the relative change and what have you, but in general, almost everybody will swim faster when you wear a wetsuit. Safety, this is an issue. If someone is going to die during a triathlon, it is going to be during the swim. And so trying to understand the safety aspect of wearing a wetsuit is important. We've actually done some research in that area. And then finally, I always like to mention, hey, not only do you have to have a fast wetsuit, but you need to be able to take it off. And you need to be able to get it off fast. Here are some pictures of some people running while taking their wetsuit off. And the pictures on the bottom are people having their wetsuits taken off by volunteers. And it's just important strategy in terms of getting the wetsuit off. Okay, to summarize swimming kinetics, we're moving in water, and water is a very dense fluid, 800 times more dense than air. There is a buoyancy force pushing upwards on the swimmer. And then there's drag forces, resistive drag, trying to resist the swimmer from moving forward. The propulsive drag is going to propel the person forward. Both of those are determined from the equation 1/2 rho CdA V squared. And the units for each of those forces are units of newtons. Okay, thanks everybody.